This is your second to last day of final prep and the last practice final exam. So this is practice final exam 4. And we'll be going through problems 1 through 4. I don't have too much to say aside from that. I hope you're all staying safe and healthy out there. And yeah, let's get into it. So problem number 1. Pretty much the same as what we've been seeing before. It has actually 2 questions inside of it. Both of them dealing with derivatives and derivative rules. This first one is looking at the derivative of square root of h of x minus g of x times the square root of h of x plus g of x. And as always, we ask ourselves, which rules are we going to use? And to do this, we work outside in, is the way I like to think about it. And if we're doing that here, we run into the product. I'm going to mark this right here, right? So really outside of all the parentheses, we have a product. That's right there. 1 second. Good. I want to make sure this is actually recording me. Okay. And the product is sitting outside the parentheses, so that means first we're doing our product rule. And then within the parentheses, the plus sign and the minus sign, we don't care about those. But we do care about the square root. So really we're going to view the square root of h of x as h of x to the 1/2 power, and all of a sudden you see an extra pair of parentheses. So each of these will have a chain rule. So that's it. We're using the product rule first, and then eventually we'll end up with the chain rule second. I'm going to work in terms of primes because I think it's a bit clearer. So I'm going to rewrite this as square root h of x plus g of x. Oops. Technically, we start with a minus, not that the order matters. Minus g of x, square root of h of x plus g of x, prime. So the product rule is going to give me derivative of the first prime, keep the second the same. Switching my plus and minus signs again. Keep the second the same. Add the keep the first the same. And then you take a derivative of the second. So I like that notation with primes. I think it's pretty clear like this. And if we were taking the derivative of the first in other ways, so I'm going to rewrite this as h of x to the 1/2 power prime minus g prime of x. And then over here we just have h of x to 1/2 power plus g of x. Boy. And then the other term, h of x to 1/2 power minus g of x, and h of x to the 1/2 power prime plus g prime of x. So let's just look at one of these terms separately. Work it out, and then we can just replace all of those terms with what they should be. So this is a chain rule, derivative of the outside. 1/2, keep the inside the same. H of x to the minus 1/2 multiplied by the derivative of the inside. Be clear about that. This is derivative of outside. Keep inside the same. And this is multiply by derivative of inside. And in case this wasn't clear for the product rule earlier, I'll make sure I talk about that here. This is the product rule. Okay, so that's what every single h of x to the 1/2 power prime is going to look like. So let's work that out here. This is 1/2 h of x to the minus 1/2 h prime of x minus g prime of x. H of x to the 1/2 plus g of x plus h of x to the 1/2 minus g of x. And finally, 1/2 h of x to the minus 1/2 h prime of x plus g of x. G prime of x there. Okay, so this doesn't exactly look like the answer that is given, so we want to maybe simplify this. So by that I mean we're going to FOIL. So if you FOIL here, FOIL the first set. So that's going to FOIL into, I guess that's 1/2 h prime x minus g prime x h x to the 1/2, or I'm doing first inside, outside last, that's fine, plus 1/2 hx to minus 1/2 h prime x g of x, and then we end up with minus g of x g prime x. So that's me foiling the first part, and then me foiling the second part is going to look like basically the same, right? Or it'll look very similar. 1/2 h prime x. This is now going to be plus g prime x hx to the 1/2, and then this is going to be minus 1/2 hx to minus 1/2 h prime x gx, and then we're going to end up with minus g of x g prime of x. And all of a sudden the what we have as an answer on our answer sheet is starting to look much clearer because that term and that term cancel, and this term and that term cancel. And so we just end up with 2 times 1/2, so that's just 1 h prime of x, minus both of the last terms. So there are 2 of these last terms, g of x, g prime x. This is the answer exam gives. Okay. So now what am I going to bring up? The thing that you guys were all probably screaming at me because you probably saw it right away. Simplify first instead. Simplify first to save time. So let's rewrite this as what it was written as right away. Prime. And we can just simplify the inside. Or if we FOIL the inside, write that out up here. FOIL the inside. What happens? We get h of x minus g of x squared. Trust me on that. It's a difference of squares problem, so that's definitely going to be the truth. So now, if I take the prime of this, I get h prime of x minus g of x squared prime. So you still have a chain rule here. So it's not super easy, but it's also not super hard. H prime of x, chain rule just says derivative of the outside is 2. Keep the inside the same. G of x to the first power multiplied by the derivative of the inside. There you go. So as always, make your life easy by simplifying first. You can see the big difference that made when you simplify first. So go ahead and try to do that if you think it might be a possibility. All right, let's do the second part here, the second question on problem 1. This is now d squared, I'm switching it up on you guys, dq squared of f of q squared plus 2q. And just as before, I'm going to work with primes. So I like working with primes. I think they're a bit clearer. So this is not too difficult, or at least I don't think so. Maybe you will think so. What rules will we have to use? Well, for the first derivative, we'll use the chain rule because parentheses. And more importantly, like the piece in the parentheses is not just the variable, right? The piece in the parentheses up here is q squared plus 2q. That's not just q sitting by itself. So as long as the piece in the parentheses is not the variable all by itself, you're going to use the chain rule. For the second derivative, we'll get there later. Okay, so let's just take the first derivative here. F of q squared plus 2q prime. Derivative of the outside is f prime. Keep the inside the same. Multiplied by the derivative of the inside is 2q plus 2. And put that in its own parentheses. So this is derivative of the outside. keep inside the same, and multiply by derivative of the inside. Boy, there we go, of inside. Okay, so that's pretty easy, right? That's the first derivative. But now we want to take the second derivative. So the second derivative is going to look like, I'll just write it out in prime. So there's 2 primes. It's going to be this piece that we just wrote times 2q plus 2 prime. And I think everybody can see this. Working outside in, we run into a product first. So we're going to need to use the product rule. Secondly, we will use a chain rule because there's still a thing in parentheses, a not just the variable itself, a piece in parentheses. Okay, and maybe I'll label these with numbers. That's probably smarter. So first we're going to do the product rule, and second we're going to do the chain rule. Cool. So let's do that. Working outside in, we're going to use that product rule first. So the product rule is going to say derivative of the first, wrote that poorly, q squared plus 2q prime, keep the second the same, plus the first, or keep the first the same, multiply by the derivative of the second. So this is 2q minus 2 prime. It's an ugly prime there. I'm going to fix it. Okay. So there's the product rule part, and then we're going to use the chain rule in this first piece. So derivative of the first, or derivative of the outside, keep the inside the same, multiply by the derivative of the inside, and then there's still this other piece. So, and on the second term, it's quite a bit easier. The derivative of 2q minus 2 is just 2. So I'm going to label this and make sure that everybody knows just where every piece is being used. This is product rule. There's the product rule, and then down here, so we're really doing the chain rule is happening here. This is derivative of outside, leave inside the same, multiply by derivative of inside. And then this other term here, these are just the same pieces there. I didn't want that. I wanted this in black. These are the same pieces. So this just drops down. So that's the same piece there. And then this is just the derivative there. And those just drop down. Everything else just drops down pretty standardly. And then we can simplify this if we want, right? So to make it look like, I guess, the computer gives us the answer, the exam gives us the answer. This is what? This is 2 f prime q squared plus 2q plus 2q squared, sorry, 2q plus 2 squared f double prime of q squared plus 2q. And that's the answer the exam gives. So there you go. Can't save yourself with simplifying on this one. It's pretty clear why not, because it's just a function of some variables. All right. So let's move on to problem 2. Once again, integration rules. And I was a bit tricky on this first one. So Q1, I'm looking at the integral of xy dx dy. So, what's really going on here? Nothing crazy is going on. I'll say that. It looks a little weird, but nothing crazy is actually going on. This is what the first week of Calculus 3 would introduce. And I don't mean to say that you guys are ready to take Calc 3, and I also don't mean to say that Calc 3 is easy. What I mean to say is this is a Calc 3 problem that you guys actually know how to answer. So let's just take it in 2 steps. Since there are 2 integrals, let's take it in 2 steps. Step 1, we're just going to integrate xy dx. And I think everybody can agree with me that the dx means we treat x as the variable, so y is just a number. Which means I can rewrite this as y integral of x dx, and everybody knows how to use the power rule to integrate x. X squared over 2 plus c. Okay, there's it's really like this, right? X squared over 2 plus c, so in some sense this is really like y x squared over 2 plus cy, but this is where kind of the Calc 3 stuff comes into play. C could technically be a function, a generic function of y, since all we require of this integral x dx is that the derivative with respect to x of the integral of x dx equals x. It's that the derivative and the integral cancel out. So you'll notice that if I took the derivative of x squared over 2 plus some random function of y, this is still equal to x since this doesn't depend on x. Just a number with respect to x. So that's really what's going on there. So instead of writing y x squared plus c of y, I'm going to write this as y x squared over 2 plus g of y. So over here, this is a constant. I'll put it in quotes. Really, it's a function of y. Okay, so that's the first integral. Step 2 is the second integral. If I'm integrating, let's see. If I'm integrating my answer, right? I'm going to integrate my answer. Circle this in yellow. I wanted yellow crayon. This piece, I'm going to bring it down here. My answer from the past was y x squared over 2 plus g of y dy. This integral, I'm now treating green. Y is the variable. And x is just a number. So this integral is actually x squared over 2 integral of y dy plus integral of g of y dy. And if I integrate this piece, this first one, I can do that pretty easily. X squared over 2 on y dy. We know how to do that. I'll get rid of this part and just say that this piece by itself, y dy, this is equal to x squared over 2 plus y, not plus, times y squared over 2 plus c. And I'm going to put that c in quotation marks again for the same reason as before. This could be a generic function of x. And so this is really equal to, well, it's x squared y squared over 4 plus this quote c, x squared over 2. But that could be a generic function of x, so really x squared y squared over 4 plus f of x. So there's your generic function of x. And the integral of g of y dy is just, I'll just call it capital G of y. If g of y can be generic, then g of y is also generic. It's just some arbitrary function. So there you go. Hence, by step 1 and step 2, this double integral, that's what we call it, x, y, dx, dy is actually equal to x squared y squared over 4 plus f of x plus capital G of y. It doesn't matter if you use a capital or lowercase g's or f's or whatever. This is the answer the exam gives. And that's kind of your reasoning behind it. I won't give a problem like this on the final. I just wanted to introduce it here. It's something that we use, especially if you're actually going into stats after this. This is something you cover in stats anyway, so you might as well cover it here. Okay, so that's I guess that's question 1 here. Question 2, I guess make that a straight line. Question 2, a little bit easier, I think anyway, because I give you a hint. So I'm looking for 2x minus 1 divided by x plus 1 cubed dx. And I say hint, use u sub with u equals x minus 1 over x minus 3, or x plus 3. Sorry, x plus 1. So let's do that. Do just that. Follow hint. U equals x minus 1 divided by x plus 1. That makes du, we need to use the quotient rule here. Equals bottom d top minus top d bottom all over bottom squared dx. If I simplify this, I get 2 on top, and I get x plus 1 squared on bottom dx. So does my my integral look like some combination of u and du? I'll circle these. Make our lives a bit easier. Circled. Oops, want crayon again. Circle that in red. Circle this in blue. I'll say it this way. Can I rewrite the integral so that both u and du show up? I mean, this is always how you would do. I mean, I would say this is always how you should do. How you should think about u substitution. Right. You should always ask yourself the question, can I rewrite the integral so that both u and du show up? Of course the answer is yes. Our integral here, 2x minus 1 divided by x plus 1 cubed dx. I'm going to rewrite it as the integral of x minus 1. I'm going to force u to show up, right? X plus 1. And then what is left over is 2 and x plus 1 squared dx. And all of a sudden everything is working perfect for us, because there's du and there's u. This is exactly the integral u du, and so the power rule gives us u squared over 2 plus c, also known as if u is x minus 1 over x plus 1, this becomes x minus 1 squared over 2 x plus 1 squared plus c. Answer the exam gives. There you go. I gave you one hard one, one easy one. And I honestly, I don't think the first one was that hard. If you had gotten this plus C, I would have given full points. Or I would give full points. So if you recognize that you should integrate in X and Y separately, then that's good enough for me. Anyway, let's move on to problem 3. Problem 3 says, another implicit differentiation problem. Suppose P minus 1, 1 minus P and Q minus 1 equals PQ. What is, it's a question, Q. What is dQ dP? So this is implicit differentiation, so we're going to follow the steps. Steeps. So see week 1 final review for steps. Step 1, we're going to take D of both sides. So if we do that here, D of 1 minus P, Q minus 1, and here D of P, Q, we have these products sitting in here. That means we're going to have product rules. So you want to think about that in all of these implicit problems. If you have a product of variables, you are going to use the product rule. So those products right there are telling you to use product rules. So that's going to say we get D 1 minus P times Q plus 1 minus P dQ, D of Q minus 1 equals dP Q plus P dQ. So really rewriting this, D, the derivative of a constant like 1, that's still 0. So this is really negative dP Q plus 1 minus P. Oh, sorry, this was Q minus 1 here. This is still Q minus 1. Plus 1 minus P dQ equals, and I'm just going to rewrite this as Q dP plus P dQ. And I'm going to rewrite these as 1 minus Q dP plus 1 minus P dQ equals Q dP plus P dQ. That's step 1. Step 2, divide by D of the variable on the bottom. On the bottom of what we want to solve. So in this case, what is that? It's on the bottom here. I say, what is dq dp? So there you go. P is the piece on the bottom. So that's dp here. So we're going to divide by dp. Divide everything, right? Divide everything by dp. What do I end up with? I get 1 minus q. dp divided by dp is just 1 plus 1 minus p dq dp equals q. dp over dp is still 1 plus p dq over dp. Step 2, step 3. Bring all terms with what you want to solve for to one side, and everything else to the other side. So my two terms with dp, dq, or dq, dp, I'm bringing to the left. So I have 1 minus p dq, dp, and then I'm bringing over the p term on the right-hand side. So that's a minus p dq, dp equals really negative 1 minus q plus q. Okay, so really what's going on here is this is 1 minus 2p dq dp, and this equals negative 1 minus q is positive q minus 1. This is 2q minus 1. Step 4 in this case is really easy because it's already done for us. Factor out what you want to solve for. And divide by the rest. So it's already factored out. I'll just rearrange it so that it looks more like what we normally have. 1 minus 2p equals 2q minus 1. Divide by the rest. In this case, the rest is 1 minus 2p. So we end up with dq dp equals 2q minus 1 divided by 1 minus 2q, or 1 minus 2p. And hopefully that's what the exam gives. Feels right to me. Did I do anything wrong? Yeah, that feels right to me. Okay. I might have written it down on my exam. It'll be right on yours. So answer exam gives. Unless I've done it wrong here, and then we'll see something else. And check this just to make sure I've done everything right. So let's see. If P is on the bottom, then yeah, then the P term should be on the bottom. That's right. Okay, good. Always nice when I have to double check my answers, right? All right, last problem for today. Problem 4. Problem 4. This is a fun problem. The numbers aren't great, but they're as good as I could make them for this. It says you are going to run a marathon, 26.2 miles. You have 2,100 kilocalories of energy that you can expend during the marathon, after which you must immediately stop running. running at v miles per hour uses up EV. So I'll just write this down. We have 2100 kcals of energy to use to run 26.2 miles, running at v miles per hour expends E of v equals v cubed minus 26.2 times 2/3 v squared plus 2100 divided by 26.2 plus 26.2 squared over 9v kcals of energy per hour. Okay, and then I asked the actual question, how fast should you run to minimize your marathon time? And I think all of you are recognizing these words now that I've written them down so often. Minimize. This means we want to optimize your marathon time. What are we optimizing? We're optimizing time. So we need a function for time dependent on velocity. So that we can do the thing that's going to earn everybody a lot of points. Change my color even, that's how it's important it is. Take a derivative. Set it equal to 0. All caps, please. Solve. Oh boy. For our variable. In this case, for velocity. All right. So we need a function for time dependent on velocity. Can I use anything here to relate time to velocity? Well, v miles per hour, I want this in crayon as well. V miles per hour at 26.2 miles, that's pretty easy, right? That means that time, t, dependent on my velocity is going to be 26.2 divided by v. There's my function of time. So I'll say C up top in yellow. Time, dependent on velocity, 26.2 divided by v. And all of a sudden, people are starting to freak out because we haven't used E yet. Let's just work with this for now. Let's optimize. So t prime, well, I'll rewrite t of v as 26.2 v to the negative 1. That makes t prime of v negative 26.2 v to the negative 2. So if we set that equal to 0, solve for v, what do we get? We get v equals infinity, plus or minus. Because of course, running at an infinite velocity would be great for a marathon time. Okay, that's not the answer though, right? It's not the answer. This is clearly not correct for a few reasons. One, nothing can exceed the speed of light. Two, it would require infinite energy, since E of positive infinity is positive infinity, and we only have 2100 kcals. And I guess three would be that it's not the answer that the exam gives. That's always a safe bet too. Maybe I'll write that down. 3, it's not the answer the exam gives. Okay, so how do I fix this? How do I actually decide how fast I should run to minimize my marathon time? Well, like I said before, we haven't used E yet, and that's kind of our known. Our known quantity. So we want to remember that remember E of V measures energy per hour. So for total energy, i.e. is 2100 kcals, we need to multiply E multiply EV, energy per hour, and TV, the number of hours. This is energy per hour, energy over hours, and you multiply it by the number of hours. All of a sudden, those cancel, and this equals energy. Okay, so we have TV here, it's 26.2 divided by V, and we have E, it's there. So let's just write that out. Sounded very Canadian with that out. EV times TV is going to be 26.2 V squared. And then we get minus 26.2 squared times 2/3 V. Then this last piece is going to be 2100 plus 26.2 cubed over 9. And then this is going to, so this is our total energy equation. And if we can expend 2100 kilocalories, then it equals 2100. So let's just examine this equation. And let's just solve it for V. To see all possible values for V. Like, is there even a possible value that I could run at so that I can actually even complete the marathon? So this will compute all possible values. The first thing I'm going to do is the 2100s cancel. So it's really 26.2 V squared minus 26.2 squared times 2/3 V plus 26.2 cube over 9 equals 0. And I can divide everything by 26.2 and make this a little easier. That's going to give me V squared minus 26.2 times 2/3 plus 26.2 squared now over 9 equals 0. Now I can just use the quadratic formula. So this gives me V equals negative B plus or minus the square root of B squared (2 squared over 3 squared) minus 4AC all over 2A. And all of a sudden, you guys are like, son of a gun, Evan, how do you get these numbers to work out? Notice that that is equal to 0. So this is just 26.2 times 2/3 divided by 2. So of course those 2's cancel as well. And I get the velocity is 26.2 divided by 3 miles per hour. That's the only possible velocity for me. So, hence also the velocity that minimizes my time. If there's only one possible, then that's the one that minimizes it as well. You'll notice that the time it took me to run my marathon T of 26.2 over 3 is 3. So it took me 3 hours to run. Pretty good marathon time, I think. I'm not a runner, but pretty sure that's pretty good. The world record is like 2 hours, but of course that's exceptionally good. So there you go. That's how you do it. It turns out there's only one possible velocity here. It doesn't seem like it at the beginning, but that's actually what's true. Okay, so that's all I have. Tomorrow's the last lecture you'll ever have from me, probably, unless some strange circumstances happen. So yeah, thanks for a good semester. I'll see you all tomorrow. Bye.